Welcome to our lecture on numerical differentiation. Imagine you are driving a car and your speedometer is completely broken, but you have a GPS recording your position every second. How do you figure out your speed? In standard calculus, we use continuous functions to find exact derivatives. But in the real world, we often only have discrete data points, like those GPS coordinates. Today, we will learn how to estimate the rate of change using only a table of numbers, a highly practical technique used across science and engineering. Now that we understand the premise, let us look at what numerical differentiation actually is. In standard calculus, the derivative represents the exact, instantaneous slope of a curve at a single point. To find it exactly, we usually need a known, continuous function. However, in real-world experiments or computer simulations, we often only possess a set of discrete data points, known as nodes. Nodes are simply the individual separated measurements we have collected, like temperature readings taken once an hour. Numerical differentiation uses the differences between the function values at these nodes to approximate the slope. Simply put, instead of finding the perfect tangent line touching one point, we draw a straight line connecting two nearby points and use that line's slope as our best guess. Before we build our approximation formulas, we must introduce the most fundamental tool in numerical analysis, the Taylor series. Why does this matter? Because the Taylor series is a mathematical formula used to predict the value of a function at a nearby point, assuming we know everything about the function at our current point. Let us say we are at a specific point, and we want to know the function's value at a point slightly ahead. We use the symbol h to represent the step size, which is the small horizontal distance between our data points. By understanding how the function behaves right now, the Taylor series allows us to step forward or backward in our data table with mathematical confidence. This concept of stepping forward leads us directly to our first equation, the forward difference formula. Conceptually, this formula estimates the slope at our current position by drawing a line to the very next data point. Let us break down the symbols. The term f dash of x is our estimated slope. The term f of x plus h is the data value one step forward, while f of x is our current data value. Finally, h is the step size, or the horizontal distance between the points. It is called forward because it looks ahead to the next point to calculate the slope. Physically, as the step size h decreases, meaning our data points get closer together, the error in this approximation decreases proportionally, giving us a much more accurate rate of change. Now that we have seen the formula, let us understand where it comes from by deriving it. We start with the Taylor series expansion for a point slightly ahead. The series includes the current value, the first derivative, the second derivative, and higher order terms. Because our step size h is a very small number, h squared is even smaller. Therefore, we can truncate or chop off the series after the first derivative term to create a simple approximation. Next, we use basic algebra to isolate the term containing the first derivative by subtracting the current value from both sides. Finally, we divide both sides by the step size h. This gives us our final result, proving exactly how the forward difference formula is constructed from the Taylor series. Having derived the forward difference, an important question arises. What if we are at the very end of our data table and there is no next point to look forward to? In that case, we use the backward difference formula. Conceptually, this is identical to the forward difference, but it looks backward in time or space. Here, f of x is our current value, and f of x minus h is the value from the previous step. We divide their difference by the step size h. We use this when we want to know the rate of change right now, based only on what has already happened. Physically, if the step size h increases, our estimate becomes less accurate because we are looking too far into the past. Just as we did for the forward difference, let us quickly prove the backward difference formula. We write a Taylor series for a point slightly behind our current position, which we call x minus h. Notice that the sign of the step size h is now negative, which changes the sign of the first derivative term. Just like before, we ignore the h squared and higher terms because they are very small. We then rearrange the equation, moving the derivative term to the left side to make it positive. Finally, dividing by the step size h isolates the first derivative. This gives the final result, providing us a mathematically sound way to estimate the slope using historical data instead of future data. We have now seen both forward and backward differences. While they are decent estimates, they are slightly skewed because they only look in one direction. This brings us to a superior approach, the central difference method. Why does this matter? Because we can get a much better estimate by looking at both the point ahead and the point behind, completely skipping the current point in our numerator. Imagine estimating the slope of a hill by looking at a point 10 feet in front of you and 10 feet behind you, rather than just looking at your feet. By balancing the data from both sides of our point of interest, this method significantly reduces the error in our approximation. Let us look at the mathematical form of this highly accurate method. This is the central difference formula for the first derivative. Conceptually, it finds the slope of the line connecting the point ahead and the point behind. The numerator is the difference between the future value, f of x plus h, and the past value, f of x minus h. The denominator is 2 times h. This represents the total horizontal distance between those two outer points. Physically, this formula is significantly more accurate than the forward or backward formulas because its error shrinks much faster as the step size h gets smaller. If you decrease the distance between your measurements, your central difference estimate rapidly approaches the true exact derivative. Before we move on, let us see this formula in action with a concrete example. A robot is moving along a straight line, and we are given its position at 3 specific times, 1.0, 1.5, and 2.0 seconds. We are asked to calculate the approximate velocity of the robot at exactly 1.5 seconds. Velocity is the first derivative of position with respect to time. Because we have data for the point ahead and the point behind our target time, we choose the central difference formula. First, we calculate the step size h by subtracting the first time from the second time, giving us 0.5 seconds. This uniform gap is crucial before applying our formula. Continuing with our calculation, we substitute our specific time values into the formula. We are evaluating at the central time of 1.5 seconds. The point ahead is at 2.0 seconds and the point behind is at 1.0 seconds. We plug in the actual position values from the problem, 4.8 meters and 2.0 meters. The denominator becomes 1.0 because 2 times 0.5 is 1. Performing the final subtraction and division, we get a result of 2.8. Physically, this means that at exactly 1.5 seconds, the robot was traveling at a velocity of approximately 2.8 meters per second. Now that we have successfully used this formula, let us understand where it comes from. We derive the central difference mathematically by subtracting the backward Taylor series from the forward Taylor series. When we do this subtraction, the current value terms cancel out and the h squared terms cancel out completely. We are left with 2 times h times the first derivative, plus terms containing h cubed. Because h is incredibly small, h cubed is microscopically small, so ignoring it causes much less error than ignoring h squared. Finally, we rearrange this equation to solve for the first derivative by dividing by 2h. This gives the final result, proving why the central difference is mathematically superior. To truly grasp why the central difference is superior, let us look at this visual representation. The black curve is our unknown function, and the dashed black line represents the true, exact derivative, the perfect tangent slope at our middle point. Notice the red line representing the forward difference and the blue line representing the backward difference. Both are noticeably tilted away from the true slope. They are skewed. Now look at the green line, which represents the central difference connecting the outer 2 points. It is nearly perfectly parallel to the true tangent line. This diagram visually proves what our math just showed. Balancing data from both sides provides a much more accurate estimate of the rate of change. So we have proven that the central difference holds for the first derivative. This brings us to another crucial concept, the second derivative. Why do we need this? Sometimes we need to measure how fast the rate of change itself is changing. In physics, if the first derivative is velocity, the second derivative is acceleration. To find this numerically, we cannot just subtract our Taylor series. We must add the forward and backward Taylor series together. This technique isolates the second derivative term, allowing us to estimate acceleration using only discrete position data. This is heavily used in engineering to calculate forces and impacts when only raw GPS or sensor coordinates are available. Let us examine the mathematical formula for this concept. This is the central difference formula for the second derivative. Conceptually, it compares the average of the two outer points against the center point to see if the curve is bending upwards or downwards. The formula uses 3 points: the point ahead, the current point multiplied by a weight of 2, and the point behind. The denominator is the square of the step size, h squared. Physically, if the current point f of x is much lower than the surrounding points, the numerator becomes positive, indicating a positive second derivative or an upward curve. As the step size h decreases, the h squared in the denominator makes this calculation highly sensitive to small changes. Let us apply this new formula to a concrete example. We will use the exact same robot position data from our previous example. We have positions at 1.0, 1.5 and 2.0 seconds. This time, we are asked to calculate the approximate acceleration of the robot at 1.5 seconds. Acceleration is the second derivative of position with respect to time, telling us how much the velocity is changing. We start by writing down the second derivative central difference formula. We substitute our specific time values, evaluating at our central point of 1.5 seconds. The surrounding points are at 2.0 and 1.0 seconds, and our step size h remains 0.5. Continuing our calculation, we plug in the actual position values given in the problem: 4.8, 3.2, and 2.0 meters. We also square the step size in the denominator, so 0.5 squared becomes 0.25. Next, we multiply the central position value by 2, giving us 6.4. This weighting balances the outer points against the center point. Simplifying the numerator, we get a total change of 0.4. Finally, we divide 0.4 by 0.25. The result is 1.6. Physically, this means the robot is not just moving, but it is speeding up at a rate of 1.6 meters per second squared. Now that we have used this second derivative formula, let us understand its mathematical origin. We derive it by adding the forward and backward Taylor series together, instead of subtracting them. When we add the series, a beautiful thing happens. The first derivative terms, which have opposite signs, cancel out completely. We are left with the current value multiplied by 2 and the second derivative term multiplied by h squared. To isolate the second derivative, we simply subtract 2 times the current value from both sides and then divide by h squared. This gives us our final result, proving how we can extract acceleration data purely from discrete position points. Before we conclude, let us look at why numerical differentiation matters outside the classroom. In the real world, we rarely have perfect mathematical equations for physical events. Instead, we have sensors. If we want to know how fast the temperature is dropping to predict a freeze or how fast a stock is crashing, we must use numerical differentiation on discrete data points. It is also heavily used in image processing. Computers find the edges of objects in a photograph by calculating the numerical derivative of pixel brightness. A sudden spike in the derivative means a sudden change in color, indicating an edge. Without these formulas, modern digital sensors and computer vision would be completely unable to analyze rates of change. Let us review the key takeaways from our lecture. First, numerical differentiation allows us to estimate the rate of change of a function using only a table of discrete data points, which is essential when continuous equations are unavailable. Second, we saw that the Taylor series is the mathematical foundation that allows us to build forward, backward, and central difference formulas. Third, we learned that the central difference method is generally the most accurate because it balances data from both sides of our point of interest. You have now covered the full topic, mastering a technique that beautifully bridges the gap between abstract calculus and real-world sensor data. Great job!